We've been talking about forces for a while now, so it's time to add friction to the mix. So, friction is defined as the force that opposes the relative motion between two surfaces. Sounds complicated. It's sort of, but not really. So, I have a surface. It's green. I have another surface. It's pink. The amount of friction I have between these two surfaces is determined by two things. One of them, as you may have guessed, is how smooth the surface is. So, if the green surface were grass, that would be much rougher than if the surface was a hardwood floor, for example. The grass would have more friction than a freshly waxed hardwood floor. Makes sense. The other thing that it depends on is how hard the two surfaces are pressing together. So, I can skim my hand lightly over a hardwood floor and not experience very much friction. But if I put some of my weight on my hand and try to move it horizontally, it's a little uncomfortable because of how much friction there is between my hand and the floor. So, we already have a word to describe how hard the surfaces press together. It's the normal force. The normal force being the force that a surface applies to an object. For surface roughness, we have to introduce something new. We're going to use the Greek letter mu. This is going to be the coefficient of friction. The higher the coefficient of friction, the more friction the surface has, the rougher the surface is. The closer to zero the coefficient of friction is, the smoother the surface is, the more easily the object glides. So, there are two kinds of friction. One kind is static friction. The other kind is kinetic friction. Static friction deals only with objects that aren't moving, for objects that are at rest. Static friction prevents an object from moving. Kinetic friction is the friction that we see a lot every day. It slows down an already moving object. This is why in real life, things don't roll or slide. Things don't go forever. Kinetic friction is always slowing them down. The expression that relates everything together, the force of friction is going to be denoted by a lowercase f. To differentiate between static and kinetic, we're going to use a subscript. So for static friction, we're going to use a lowercase f, subscript s. Static friction is equal to the coefficient of static friction times the normal force. Pretty easy. The kinetic one is very similar. We're just going to say F subscript K is equal to the coefficient of friction for kinetic times the normal force. So the coefficient of frictions, there's two kinds. There's the coefficient of static friction, which applies for objects at rest, and the coefficient of kinetic friction, which applies for objects in motion. The coefficient of static friction is always going to be greater than kinetic friction. That just makes sense, otherwise things might just start suddenly moving on their own, and that doesn't happen. So the coefficient of static friction, the amount of force required to overcome static friction and to get an object moving, is less than the friction that occurs when the object is already moving. So, let's talk about static friction. Let's say that I have a block on a table. The block is 5 kilograms, so its weight will be 50 newtons. Now, this block is not levitating or falling through the table, which means that the forces in the vertical must be balanced. The table is going to apply a normal force, and that normal force must be equal to the weight. So, they are both 50 newtons. Let's say I want to know how much friction is acting if I don't do anything to it. If I don't push the block, or pull the block, or really do anything to the block's acceleration is 0. So my forces are already balanced. If I added a frictional force, that would actually unbalance everything. So my frictional force, if I don't touch it, must be 0 newtons. Logical. The key point here is if I don't push on the block, friction can't push back. So, let's make things a little more interesting. Let's say I do push on the block. Let's say that I push it 20 newtons to the right. So, since the block isn't already moving, we have to do an extra step that we wouldn't normally do. We have to find the maximum amount of static friction. We know that friction is going to push to the left and try to oppose my force, but we don't know how hard it's going to push. So the maximum it can push is given by F sub s is equal to mu s times the normal force. So I said that my mu sub s was 0.6. So 0.6 times 50 newtons is equal to 30 newtons. So the maximum force that could push to the left would be 30 newtons. So my applied force is 20 newtons. It is less than the maximum possible static friction. So in this case, static friction wins. I don't get to move the block. So we know that I lost this battle and that the block's not going to move. The block's not going to move. That means there is no acceleration. Looking at our diagram, we can write Newton's second law. The sum of the forces is equal to 0. My acceleration is 0. The sum of my forces must be 0. So I'm applying 20 newtons to the right. In order for my forces to be balanced, my static frictional force must be 20 newtons to the left. And that way the forces are balanced. So notice that it didn't push with all of its possible 30 newtons. That would be kind of weird. I push on the block with 20 newtons and suddenly the block pushes back on me with 30 newtons and knocks me over. That doesn't happen. Static friction pushes only as hard as it needs to keep the object from moving. It doesn't need to push any harder than that, otherwise the object would bounce back and hit me in the face. Thank God that does not happen. So, we have seen what happens when our applied force is less than the maximum static frictional force. So, instead, let's say that I push with a force of 40 newtons. So our max was 30, I'm going to push with 40. Things kind of get interesting. So, if I apply 40 newtons of force to the right, that's more than static friction can push back. So, when my applied force is greater than or equal to my maximum static friction, the object is going to move. You would say that I overcame static friction. So now that I've overcome static friction though, I'm not in physics world. I still have kinetic friction to worry about. So now, instead of static friction, I have kinetic friction. F sub s turns into F sub k. So kinetic friction is actually a little easier to deal with. You don't have to find the maximum. You just immediately say that kinetic friction is equal to mu of kinetic friction. I guess I should give us one. Let's say that it's 0.3. Kinetic friction is always less than static friction. I just picked a number. We'll usually give you a number or ask you to solve for this number. So 0.3. And then So my coefficient of friction times my normal force. I'm plugging in my numbers. 0.3 times 50 newtons. I get 15 newtons. So I have 15 newtons pointing to the left due to kinetic friction. I can find the acceleration of my block now using this diagram and Newton's second law. The sum of my forces is equal to mass times acceleration. So my pulling to the right is going to overcome friction. We already know this because it's moving. So positive 40 newtons minus 15 newtons is equal to 5 kilograms times the block's acceleration. I will solve for A. 25 newtons divided by 5 kilograms. That is equal to 5 meters per second squared. So the block accelerates 5 meters per second squared to the right. And that is how you solve a Newton's second law problem with friction.